Thank you for joining our course on the introduction of mud crab vertical farming. In the previous lecture, we've talked about disease control using UV reactors and even ozonation. We have covered the consideration to design your UV reactors and how to incorporate them with your unit processes. Up to this point, we have covered the different unit processes that you require in any recirculating aquaculture system, starting from solid removal, which accounts for settable solids and suspended solids, followed by biofiltration, and lastly, disease control via UV reactors. In this lecture, we will be showing you how to integrate each unit processes together to form what we call a recirculating aquaculture system. This diagram shows the process flow diagram of our system. Note that we have modified the system that came from China to suit our needs. We first start off with crab houses. So our capacity is for 1,000 crab house. Waste from the crab houses will then flow through what we call the first retention tank, in which any floating solids will be removed, and any solids that sink to the bottom will go into the pump, followed by a check valve and into the sand filter. The first part of the system consists of what we call solid control, where the crab house and the retention tank will serve to remove any settable solids, whereas the sand filter acts as a method to remove any suspended solids. As we mentioned earlier on, due to the huge pressure loss across the sand filter, you would require a pump to do so. After pumping through the sand filter, the water is used to aerate and turn the biofilters. And this is where all my moving bed reactor media sits. After biofiltration, another pump is used to pump it up to the UV filter and recycle it back to the crab house. And the water is being recycled this manner. Note that we are utilizing a 2-pump system instead of a single pump. And the sand filters are being backwashed daily with tap water in order not to waste any salt water. The biofiltration is being agitated with the pump, and it also has a venturi at the end to perform what we call aeration as well as circulation. This is the boxes we are using. It is bought from China by this company called Zhongkehai, and I believe it's available on Alibaba.com. Please note that there are other suppliers who can supply boxes, or you could even DIY your own boxes on your own. The dimension of our boxes are as follows, and we have also carried out the CAD drawing to simulate how it looks like when you fit up together. Sometimes it is difficult to get the dimensions from the suppliers, and hence we have provided you with all the dimensions. This is our technical specs for all of our equipments that I am using. The centrifugal pump is about 29 meter cube per hour, whereas the total amount of volume of water in our system is about 40 meters cube. So this will mean a recirculation rate of at least twice every hour. And the pump is resistant to salt water. The sand filter breakdown, as shown as earlier, shows the breakdown of the different sands that we are utilizing in our sand filters. This is the retention tank volume of water and the biofilter volume. Note that we have 0.8 meter cube of media. For every media, we know that it can process up to 6 kilos of feed. So 0.8 meter cube would mean feeding up to 4.8 kilos a day. And this is the surface area for every meter cube. The moving bed bioreactor is agitated and aerated using a submersible pump, and as well as the pump that is used to pump through the sand filter. The amount of water we have in the system will consist of what we have in individual boxes, which is about 7 to 7.5 liters per box. And 1,000 box will give us 7.5 meter cube, plus the retention pond, plus the volume in the moving bed bioreactor, as well as the sand filter, which approximately gives us about 14 meter cube. Water is being cycled through the system at about 0.5 hours, which is half an hour per cycle. We have previously run this up to a maximum of about 700 to 800 crabs with organic loading of 300 to 400 kilos. We will now look at the important process control that you need to take care when you're running the RAS systems for mud crab. Essentially, the crabs needs to be found at a balanced state. pH, dissolved oxygen, alkalinity needs to be sufficient in order to ensure that the crabs are farmed in a healthy condition. Another important parameter is salinity, which is the amount of salt that is dissolved in a body of water. Temperature is also a relatively important concept, followed by ammonia, NO2, and NO3. This is the specific operating envelope that we are utilizing. pH needs to be controlled anywhere between 7.5 to 9. In our case, we are using about a pH of 8. If the pH is lower than 8, we usually add dolomite into the system. Dolomite is commonly used in agriculture, and it is what we call magnesium and calcium carbonate. If the pH is too high, we usually perform some sort of backwash and top up the water. But this is usually not the case, because pH is usually dropping instead of increasing. Salinity. The optimum salinity that you'll be looking at is about 16 to 17 ppt. We can run anywhere up to 10 to 25 ppt, and that's fine. However, if you're running your high salinity and you have a lot of leakage in your system, sometimes adding salt will be very costly. For those who are planning to do this near the coastside, you will have a free access to seawater, and what you could do is to dilute seawater with a little bit of fresh water to achieve your salinity. The minimum salinity you need will be around 10 ppt or even lower, like 8 ppt, but we wouldn't recommend to do so. Providing the crabs with about 16 ppt is what we feel the optimum. For fattening, soft shell, and for grow out, you might want to run at a higher ppt. Dissolved oxygen. In general, you will require at least 5 ppm to do so. However, if your oxygen is insufficient, usually it would not harm the crab, but instead it will affect your biofiltration. As mentioned earlier on, biofiltration relies on the availability of oxygen, and it usually requires at least 4 ppm to function well. In the case that you have low oxygen, do increase the amount of aeration you have in your system, either by incorporating air pumps or utilizing more venturies to increase airflow that is into the system. Temperature. The optimum temperature we found is somewhere to be 27 to 29 degrees Celsius. If the temperature is too low, your crabs will not molt that frequently. Ammonia, NH3. As mentioned earlier on, the goal of biofiltration is to convert ammonia to NO2 to NO3 as fast as possible. Ideally, you want your ammonia to be as low as possible, lower than 0.25 ppm, ideally 0 ppm. If in the event that you have high ammonia, do perform some sort of backwash or partial water change to change out the water, top up with new water. And to ensure that your biofiltration is working properly, make sure that the biofiltration process has enough oxygen, at least 4 ppm. Nitrite, NO2. Ideally, nitrite has to be as low as possible as well, in the range of lower than 0.5 ppm. Please note that the lethal dosage for nitrite varies with salinity. In a freshwater condition, nitrite is more toxic than ammonia because nitrite will bind with what we call the hemolymph and suffocate the oxygen. So this is known as called blood toxicity. Whereas if you're in a saltwater condition, greater than 15 ppt, the lethal concentration for nitrite increases because chloride ions will compete for the space for nitrite, rendering the organisms more resistant to nitrite in a saltwater condition. In the event that you have high nitrites, do perform some sort of water change to reduce the concentration levels. Nitrate is the last part of the nitrification sector. Usually, nitrate, NO3, is not that toxic as compared to NO2 and NH3. Concentration can go up to 500 ppm without harming the crabs, but ideally it should be as low as possible. Alkalinity. Alkalinity is what we call buffering capability, and ideally it should be more than 120 ppm. In the event that your alkalinity is low, do add in what we call dolomite or even sodium bicarbonate to increase the alkalinity. Alkalinity is what we know as the buffering capability of the liquid. With high alkalinity, your system is able to buffer against fluctuation in acidity. The key to controlling pH is to make sure that alkalinity is high. Lastly, calcium. RAS system designed for crustacean is very different from farming fish or other species because crabs will uptake calcium from the water. One good way to maintain enough calcium in the system is to add dolomite, or calcium chloride will do the trick as well. Ideally, you want to be maintaining calcium about 200 ppm. We have run calcium levels from 120 to 400 ppm and it's fine. Ideally, you want the calcium to be as high as possible, which is in the range of 4 to 500 ppm. Inadequate calcium levels will often result in shell thinning effect of the crabs, and it will also impact the osmoregulation of the crabs. Sometimes some farmers will actually complain that after fattening their crabs for 1 to 2 weeks, they will realize that the weight of the crab decreases. This is likely due to the lack of calcium in your system, as the crabs are utilizing their shells in their body and uptaking calcium from their shells to perform some sort of osmoregulation. Lastly, we provide standard operating procedures on when to take specific readings of the mentioned criteria. So for readings like DO, pH, and temperature, salinity, you could use what we call a digital probe or even test kits to measure this. If you are using a test kit, so it will make sense for you to take multiple readings a day. For ammonia, NO2, NO3, usually we are using chemical test kits, mainly from SARA. So for these readings, you can take them on a daily basis or every alternate days. Alkalinity, we are utilizing a titration kit. We can take it every other day, as well as calcium. Magnesium and iodine are not key values and you can take them every week. For the SAM filter, we're recommending backwashing every day for 1 to 2 minutes. So that's all for this lecture. In the next lecture, we will start to embark our journey onto understanding the biology of mud crabs and how to tune your RAS system specifically to suit the needs and the fundamental requirement of the animal. Thank you.